Salutations! This is Team Power Outage, and we are here to tell you about our project this semester in Senior Design 2. But first, we're going to give a little background, then we'll go over some of the more detailed technical design stuff. So, we wanted to do a project that had to do with power management, and our brainstorming led us to the idea of using light bulbs as an analog for larger devices that use a much larger load. We also were motivated by the idea that power generation is limited in nature, and we wanted to answer the question, how can a utility satisfy demand for transient loads or loads that aren't present all the time on the grid? So how do we define success for this project? We want our system to be able to accurately measure the loads that it's supplying, because if it can't accurately measure the loads, then it won't know which loads draw how much power, and we obviously don't want to overdraw. So in addition, we want to be able to detect significant changes in that power draw mid-test, because if a load changes in the real world, a power utility is going to want to know that as soon as they can. In addition, the system must be able to calculate which combinations of loads can be powered simultaneously in order to reach the energy or time goals that they're trying to meet as efficiently as possible. We decided to use 4 different tracks, and we say tracks because we're actually using track lighting fixtures in our project, but all we mean when we say track is a line of light bulbs that count as one load. So we're using 4 different tracks or loads that contain variable light bulbs in them that each draw different amounts of power. This lets us vary the amount of load on each track. Then we use current transformer circuitry to measure the power draw of each individual track. It does that by measuring the current going to each load, and that signal gets sent to a microcontroller, which is then programmed using the knapsack algorithm to derive a method of delivering the required joules to each track as efficiently or as quickly as possible. And once that algorithm is finished, instruction signals are sent from the microcontroller to relays that are attached to each track, which control the connection of the separate loads to the power source, which is, in this case, the wall.
So I'm going to talk a little bit about the hardware used. We started off by cannibalizing an extension cord, which allowed us to grab a power source from the wall. We put this through an electrical box and used that as a branch to branch out to 4 separate lines. These 4 lines had current transformers and inline amp, volt, and voltmeters on the lines in order so that we could prove the concept that we were trying to create. We also used relays, we'll talk about those a little later, to cut the power on and off. In the midst of all of this, we developed a hardware shield, and we used this hardware shield to separate our high voltage and low voltage wires so that we wouldn't have any crosstalk happening.
The system wound up having 4 subsystems. The first was the current transformers and the circuitry that goes along with them, as well as the actual voltmeters and ammeters that we attached to each line. The current transformers themselves use a 1,000 to 1 ratio, which means if 1,000 amps are going through the line, hopefully not, then 1 amp will be output from that current transformer. Those transformers are attached to a low-pass, full rectifying circuit, which creates the voltage signal that goes into the TIVA, and that leads us to the second subsystem, which is the knapsack solver. This is, more than anything, it's a piece of software being written on the TIVA microcontroller, which solves that knapsack problem, and it determines which loads can be powered simultaneously and in what order. The third subsystem is the relays themselves, and all they do is connect the power to the loads based on the signals that they receive from the microcontroller. And lastly, the fourth subsystem is the loads themselves, which just turn electrical power into usable light because they're light bulbs.
Moving on to the current transformer subsystem, our loads in this case are AC, but our microcontroller reads in DC voltages. In addition to that, a maximum voltage that the TIVA can read in is 3.3 volts. In order to correct this, we use the full wave rectifier with a low pass filter that changes our AC signal into a DC signal no more than 3 volts. The way that we determined what those components were going to be was we decided based on our wattages what our max AC signal was going to be, and then using LT Spice we calculated what would give us a 3.3 voltage maximum. Moving on to the relays, this is essentially a switch. There's 4 relays total controlling all 4 loads, and the TIVA controls the relays with 3.3 volt signal. We have it set to normally open with a external DC power supply of 5 volts at 2 amps. And based on the voltages that are read in by the current transformer, the TIVA will tell the relays to turn on and off, turning the loads on and off.
The first step for the control algorithm is to detect the wattage on each line. So it will turn on one device at a time, device 1, device 2, device 3, and device 4. And it will save those wattages that it detects, 50, 75, 183, and 224. These wattages it then tries to fit underneath 270 watts using our knapsack algorithm. So device 4 will be turned on by itself. Then device 3 and device 2 will be turned on at the same time because summed together they are underneath 270 watts. There's device 4 on, device 3 and device 2, and then device 1 will be turned on, and there's enough leftover wattage that device 2 can be turned on as well. It will continue to cycle through these different devices, giving them power one at a time, and also increasing the total energy sum in watt seconds on each device. There's also the total amount of time that each device has been running, as well as the total time. The first device to reach its goal, we'll see here in a minute. Now device 4 is at 4444 watt seconds. So right now it passed its goal. Its goal was 5,000 watt seconds. It's now past that goal, and so it will recalculate the it will recalculate the knapsack algorithm. And what we notice here is that device 2 has also passed its goal. And so the only ones left are 1 and 3, which can run at the same time. Device 3 will then pass its goal now, and device 1 runs on its own to completion. Now that all 4 devices have had their energy goal satisfied, it turns off. The second demonstration is the same as the first one, besides the fact that the goal energies have been changed, so that device 3 has a higher energy demand than goal 2. It'll take more seconds in total for device 3 to complete, so whenever the knapsack algorithm runs, it knows to put a higher priority on 3 than device 2. We'll see how this plays out in a moment. So first again, it runs through all 4 devices and saves a very close wattage to the last time, only a few watts variance. It determines, again, 4 to run first. Device 3 and device 2 run second. Now you notice the difference this time. Device 1 runs, but instead of device 2 running at the same time, device 3 does, because device 3 has a higher energy goal than device 2 when divided by the wattage. So we will see these continue playing out through the same cycles. I'm going to skip ahead a little bit in time. So now, this is the last cycle for device 3 and 2. We will see device 3 turn off. So right now, what just happened is device 2 and device 3 were on. Device 3 met its goal, and it turned off. The knapsack algorithm reran, calculated that device 4, device 2, and device 1 still need to run. So device 4 is now running. Now device 4 met its goal, so the knapsack algorithm runs again. It determines that this time only device 2 and device 1 need to run, and they can run at the same time. Device 2 will now meet its goal, and device 1 runs to completion. Taking a total time of 81 seconds.
Finally, in conclusion, I will mention some of the weaknesses and the strengths of our project. The system itself is not portable. We haven't tried moving it around that much, especially not since we've got it working, but it could be a little more permanently assembled. Moving on to the strengths of our project, we were able to assemble the project, a working version of the project, for around $400, which was our budget. So the cost of actually producing this system was certainly a strength. And lastly, the system itself is very modular. I mentioned that we are using 4 tracks for the knapsack solving algorithm, but the program itself that ECE wrote has been tested using 7 simulated tracks, and it still worked as expected. So that's our project, and thank you for listening.